Hello, we have learned that if we have a point mass m, it's going to produce a gravitational field centered around it, whose field strength can be calculated using the formula gm over r squared. Now, what about the planet Earth? The planet Earth is not a point mass, but we can always pretend that all its mass is concentrated at a point at the center of it. Then we can still use the formula g over r squared to calculate its field strength at distance from the center of the Earth. So if I plug in the mass of the Earth and the radius of the Earth, guess what number I'm going to get? 9.81 newtons per kilogram. You're of course very familiar with this number because that's the gravitational field strength on the surface of the Earth here. As we move further away from the center of the Earth, the field strength of course decreases. It decreases according to the inverse square law, but it doesn't quite drop to zero, you know. After all, that's what kept all our satellites and even the moon, orbiting around us. If the Earth is indeed a point mass with all its mass concentrated here, then the field strength, the graph will continue to rise up here. But the Earth is of course not a point mass, so this formula is applicable only for positions above the Earth, outside the Earth. In fact, as we go deeper into the Earth, the field strength actually doesn't increase, it actually decreases. Why is that so? Suppose you are here. If you are here, actually this part of the Earth is actually pulling you up. It's only this part of the Earth that's pulling you down. That's why as you go deeper and deeper, the field strength actually decreases. In fact, right at the center here, when the Earth is pulling you in all directions, the resultant gravitational field strength is actually zero. If you assume that the Earth has got a uniform density, we can actually show mathematically that the gravitational field strength varies linearly. But then this is not in your syllabus, so you don't have to know this. What you have to know is that the gravitational field strength on the surface of the Earth is actually constant, 9.81 newtons per kilogram. That's because where do human beings operate? We operate here on the surface of the Earth. Even if you climb the Mount Everest or you dive into the deepest ocean, you're just moving maybe 8 kilometers, 10 kilometers both ways. So you're always about 6,400 kilometers away from the center of the Earth. That's why the field strength is practically constant at 9.81 newtons per kilogram and it's always acting vertically downward. But having said that, is the field strength really uniform across the surface of the Earth? No. We have already mentioned the mountains and the valleys and the oceans. Yeah, that's one thing. But actually, the Earth itself is not even spherical. It kind of have a bulge around the equator. So this picture is very exaggerated, but because of the bulge, the gravitational field strength at the poles is actually stronger and the gravitational field strength on the equator is actually weaker. Besides this, the density of the Earth is also not uniform. So if you measure the gravitational field strength to be stronger, unexplainably stronger than what it should be, then maybe you're standing on top of a gold mine. Conversely, if the gravitational field strength is unexplainably low, then maybe you're standing on top of an oil field. But the most interesting reason for the gravitational field strength to vary across the Earth's surface is actually the rotation of the Earth. Because of the Earth's rotation, the gravitational field strength is actually weaker at the equator. I'll explain that in another video. Alright, ta-ta!